A short discussion on polar coordinates. Now, the first thing to remember about polar coordinates is it's different than Cartesian coordinates. And you'll notice the graph paper is significantly different than the rectangular coordinate system. So here we have a bunch of concentric circles centered at the origin, and the green line here, the solid line, is what's considered the terminal side of the angle. And the red dotted line is the opposite side of the terminal angle. And basically what happens here is this is the x-axis, and obviously the right-hand side is positive and the left-hand side is negative. The problem is we're going to rotate the x-axis, and we have to remember which side is the positive side. So the positive side is always the terminal side of the angle. So if I move the angle to be a little bit positive, you'll see that the x-axis is rotating. And obviously, the right-hand side is positive and the left-hand side so far is negative. But when we get to past 90 degrees, the positive side is now on the left-hand side because that's the terminal side of a 2.2 radian measure angle. And then the other side is going to be considered negative side of the x-axis. So we're going to measure out on these axes the radius of a circle, basically. So you can kind of imagine what's going on here. The positive side is always the solid side, and the negative side is always the dotted side. And the angle of opening is this piece right here. All right, so let's see what happens if we try to plot a point in polar coordinates. So I have a couple of examples. So we're going to start off with pi over 3. Now, pi over 3, this graph paper is split into pi's over 12. So from here to here, that's 1 pi over 12. That's 2 pi over 12, also known as pi over 6. That's 3 pi over 12, 4 pi over 12, and 5 pi over 12. 4 pi over 12, better known as pi over 3. And then 5 pi over 12, 6 pi over 12, better known as pi over 2, and so forth and so on. So the first thing we have to do is find this pi over 3. So pi over 3 is 4 of these. So this is pi over 3 right here. So I'm going to type in here pi over 3, and it'll put my terminal side where it belongs. And the 3 here is the amount of radius that we have to attach to it. So we need to move out 1, 2, 3. Now be careful, in some computer programs they'll do like 1 and 0.5, 1.5, I'm sorry, 0.5, 1, 1.5, 2. So be careful of the scaling factor of these circles. But this one is 1 by 1, so we just have to go here. And this is where the point would be plotted. So that would be there. So it's 3 units away from the origin, and it's 60 degrees, or pi over 3 radians, above or measured away from the x-axis. And that's it. That's pretty easy. So it only gets tricky when you have negatives involved, like this -4, 3 pi over 4. So again, we're going to rotate our angle to 3 pi over 4. So this is 1 pi over 4. This is 2 pi over 4. This would be 3 pi over 4. So we're talking about this being our terminal side. All right, so let me type that up here. Get our angle in the right place, 3 pi over 4. And it puts us exactly where I said. And here it says -4 is our radius. Well, obviously, kind of makes no sense to have -4 as a radius. But basically all it means is you're not going to count out on the solid terminal side of the angle. You're going to go the opposite direction. So we're going to go 1, 2, 3, 4, and this is where we're going to plot our point down here. That would be this one. So it's 4 units away from the origin, and the measure of the angle is opposite of a 3 pi over 4. Now another way of writing this coordinate would be a -pi over 4, and then the radius would be solid here. This would be the terminal side. So the same coordinate can be reached by 4, negative pi over 4, or if we wrap around all the way this way, then that would be 7 pi over 4, and it would be 4 comma 7 pi over 4. So polar coordinates are interesting in the fact that they're not unique in writing them because we're just wrapping around circles here. So location is the most important part. So be very cautious of that negative. It's opposite the terminal side. So let's talk about changing a rectangular coordinate into a polar coordinate. So let's say we start off with a point in the first quadrant. Let's just call it AB for the fun of it. So if I have this rectangular coordinate of AB, let's say it's located here. If we attach it to the origin, drop a side and make a little right triangle out of it. And if this is the coordinate A comma B, then this side of the triangle is A, because that's an x distance away from the origin to underneath the point. And then this is B, how tall it is along the y-axis. So in this triangle, we're going to create an angle. So here's theta. And for polar coordinates, we're going to write things as r theta. So the radius of a circle and the angle of opening from the x-axis. So you have to kind of imagine there's a circle here that this terminal side is creating, and theta is the opening, and r would be this side of the triangle. So that would be the radius of the circle. All right, so a couple things that we need to find. Well, r is a good one to go looking for. But we also want to relate a and b to r and theta. So let's just set up some trig. One thing we can set up is we have a theta, we have a b, and an r. Let's start with a. We have theta, a, and r. So according to theta, a is adjacent, r is hypotenuse. So that would be cosine of theta is equal to a over r. And similarly, if we look at theta, b, and r, that would be opposite over hypotenuse, which would be sine. So we would get sine of theta is equal to b over r. All right, so if we solve for a, we would get a is equal to r cosine of theta. So the x-coordinate of our point is going to be r cosine theta, and b, being the y-coordinate, would be r sine of theta. And this looks really familiar to the coordinates of a unit circle, where the x-coordinate is cosine and the y-coordinate is sine for a unit circle. And then this radius just gets multiplied in there, and it gives us our new x and y coordinates. So a relationship that we can use is that x coordinate is the same thing as r cosine theta, and the y coordinate is the same thing as r sine theta. All right. Another thing we can get from this picture, we haven't even talked about changing a rectangular into a polar yet, but information from the picture that we can obtain is a relationship for just theta itself. So let's say r was not even in the picture, then all we have is a and b, also known as the xy coordinate. So if we're talking about theta and b and a, that would be opposite over adjacent. So we would have the relationship of tangent of theta is equal to b over a. And therefore, theta is equal to tan inverse of b over a. Now that gets a little bit tricky because tan inverse only works in quadrant 1 and quadrant 4. So we have another formula that relates between polar coordinates and rectangular coordinates, thetas, r's, x's, and y's. All right, so these are three of the main ones. The last one is actually the simplest one. It's literally just the Pythagorean theorem. So it's x squared plus y squared is equal to r squared of that triangle. Okay, so using these four formulas, we should be able to change a rectangular coordinate into a polar coordinate. So for example, let's look at a simple point, 2, 5. If you want, we can plot it rather quickly. 2 to the right, 5 up, and our triangle would look like this. Now, if you ever get confused between polar coordinates and rectangular coordinates, I highly suggest drawing the picture, especially when it moves into the second quadrant and beyond, second, third, or fourth. All right, so this side is 2, this side is 5. So the two things we need to find to change it over to r theta is the radius, which happens to be the hypotenuse of this triangle, and the angle, which is right in here, this angle. Okay. So to find the third side, we're just going to use Pythagorean theorem. So that comes in really handy. So it would be 2 squared plus 5 squared is equal to r squared. Therefore, r is going to equal the square root of 2 squared plus 5 squared. And r is equal to 4 plus 25, square root of 29. So the radius of the circle that goes through this point is going to be the square root of 29. All right, so the second part of it is the theta. So theta, to find that, is we're going to use this formula. So theta is going to equal tan inverse of y over x, which would be 5 over 2. And then we'll use our calculator of 5 over 2. Depending on, again, if it wants it in radians and degrees, make sure your calculator is in one mode or the other. This one's in degrees right now. So it's 68.2 degrees. So theta is approximately 68.2 degrees. And I'm writing that down really quickly because that's what my calculator told me. Now, this is where you have to be very, very cautious. Tan inverse, if you remember from back a few sections, only works in these two quadrants, and it only literally works from 0 to pi over 2. So if you're in the first quadrant, your answer has to be between 0 and pi over 2. And if the angle's in the fourth quadrant, your answer has to be between 0 and negative pi over 2. You can't wrap around. It has to either go up or go down. It's the only two options. So that the calculator is telling me the angle's in the first quadrant, I have to verify that the angle really is in the first quadrant. So this picture over here shows my triangle in the first quadrant, so I'm going to trust my calculator this time. So the r theta for this point is going to be the radius, square root of 29, and the angle, 68.2 degrees. And that would be the same thing as the coordinate 2, 5, the same location, literally right on the same point. So let's see where the calculator is going to not do exactly what I want it to do. So here I have a point, -3, 7. And one thing later that we have to talk about is, how do I know this is a rectangular coordinate? And the answer is, you don't know unless it says so. This could be a polar coordinate also, where 7 is like 7 radians or 7 degrees. If it's radians, since it's a unitless measurement, you don't have to write anything after it. So we kind of have to be told what system we're starting in to convert it into the other one. So here I'm guaranteeing that -3, 7 is a rectangular coordinate. So -3, 7 would plot right about, let's guess here. And again, I highly suggest drawing the right triangle to help you get the correct answer. So the x value is -3, the y value is 7. This is the point -3, 7. And we need to find the two pieces of information for r and theta. So we want to convert this into r and an angle, the radius and the angle. So the easier of the two, of course, is r. So if you want, you can switch the formula around to be r squared equals x squared plus y squared, since we're solving for r to begin with. So r squared is equal to, careful with the negatives, since we're squaring them, sometimes it's better just to leave the negative off. So it would just be 3 squared, which is the same thing as -3 squared. So we're going to get r squared is equal to 9 plus 49, which is 58. So that would be the square root of 58. All right. So the hypotenuse of this triangle is the square root of 58, but that's also the radius of my circle that is passing through this point. So we know what r is. That's the square root of 58. Now theta is going to be a little bit more tricky. So let's do this color. So theta formula is tan inverse of y over x, so it's 7 over negative 3, so you can write it as negative 7/3, or you can write it as 7 over negative 3. Either one's fine, just don't lose the negative sign. All right, so if I get to my calculator and do tan inverse of negative 7 over 3, so tan inverse of negative 7 over 3 gives you negative 66.8 degrees. And negative 66.8 degrees would put us down here in the fourth quadrant. But that's not where my picture is. And this is where it's really important to have the picture so you can recognize that the answer the calculator is giving you is not the answer that you want. So to fix this, all we have to do is move our angle from here back to where it belongs, which is way over here. And that's a straight line rotation, so this is just pi away. So if I add pi to my answer, then I should end up in the right quadrant. Or, well, I'm sorry, 180 degrees away. So if I add 180 degrees to my answer, then I should end up in the right quadrant. It moves me from the fourth quadrant up into the second quadrant, and it'll give me the same reference angle because opposite angles are congruent. All right, so let's add 180 degrees to my calculation. So plus 180 degrees. So that's 113.2. So the angle that we have to use for theta is 113.8 degrees, 0.2 degrees. Okay, so negative 3,7 in rectangular coordinates becomes square root of 58 comma 113.2 degrees in polar. And they're still talking about the same point up here. This location right there is exactly the same for both of these systems. Here's a situation where if we're changing a polar to a rectangular, sometimes it's not best to draw the picture. I'm going to go ahead and draw the picture anyways, just to get you used to plotting this coordinate negative 4, 3 pi over 4. So first off, 3 pi over 4 is in the second quadrant because the 4 tells me to cut the top into 4 equal pieces, and we're going to go 3 of them. So the terminal side of 3 pi over 4 would be someplace over here. Now remember, this is the positive side of the axis. So what's going on is we have to go negative 4, so we're going to have to go out the back way. So negative 4 distance along this line would put us someplace down here. So this is the location of the point. So if we drew this as a triangle, we would get this picture. So our whole point is to get down here in the fourth quadrant. So we have to have a positive x and a negative y. All right, so we know the reference angle, and we want to be really clear about, this reference angle. This is pi over 4 going down. Another way of writing this coordinate, instead of negative 4, 3 pi over 4, sometimes it's easier to write it as 4 negative pi over 4 to get it, going in the right direction. It's going down pi over 4 and out along the radius 4 units. So these are the same point. All right, so if this is pi over 4, then this side is negative 1, this side is 1, this side is square root of 2. It's a special triangle, and the only reason I'm writing that is I know what formula I'm going to use. I'm going to use the relationship that x is equal to our cosine theta and y is equal to our sine theta. Okay, so by the first one, -4, 3 pi over 4, we got to be careful. The 3 pi over 4 puts us on the second quadrant angle, and the -4 just tells us our location is over here. So if we're going to do cosine and sine of 3 pi over 4, I really need to draw my special triangle in the second quadrant. So sometimes it's better if you change your radius from negative to positive just so you can avoid that situation. So I'm going to use this point over here rather than going back to the other one. And then I'll just show you a different way of doing it. So by the picture, then we get x is equal to 4 is my radius, cosine of negative pi over 4. And over here, I'm going to go y is equal to 4 sine of negative pi over 4. Now, putting the negatives in allow me to put that negative in my answer. So if it was just pi over 4, it would be in the first quadrant. The answers would both be positive. And I don't want that. So this is going to be x is equal to 4 times cosine of the picture over here, which is adjacent over hypotenuse, which is square root of 2 over 2. And this reduces to 2 square roots of 2. So my x-coordinate is positive. And y would equal 4 times the sine of this picture, which would be -1 over square root of 2, opposite over hypotenuse, also known as negative square root of 2 over 2. And this answer would be -2 square roots of 2. So the coordinate in rectangular form would be 2 square roots of 2, comma, -2 square roots of 2. Which puts us in the fourth quadrant. Now, the other way of going about it, which some people will prefer, let's say we're going to change -4, 3 pi over 4 from polar into rectangular, xy. And if we just did it by the formula to start with, this would be -4 times cosine of 3 pi over 4. And then this one over here would be y equals -4 sine of 3 pi over 4. And then if we were going to go for an exact answer, we would draw a special triangle. Well, let me not draw it there. Let's put it up here. We would draw a special triangle. We'd put it in 3 pi over 4. We know the reference angle here is pi over 4. This side is -1, this side is 1, this one is square root of 2. So if we went this route and kind of ignored the -4 and just concentrated on the 3 pi over 4, this would be x is equal to -4, and then the cosine of 3 pi over 4 would be -1 over square root of 2, also known as negative square root of 2 over 2. The y would be -4, and the sine would be opposite over hypotenuse, and it would be positive square root of 2 over 2. So again, we would get a positive x and a negative y. And we would end up at the same coordinate, even though my picture really doesn't correspond to the location of this point. So this would be the xy coordinate. You'd be over here someplace. And it corresponds to what we did earlier. And again, you could type it in your calculator. The only problem is this would be in decimal format. You'd probably have to round it. These would give you the exact coordinate. This method. Now, if it was an angle that is not a special triangle, guaranteed the only way to do it right now is by calculator. Well, since we can talk about coordinates, I guess we should be able to talk about graphs also. So here I have y equals 2x plus 3. It's a nice simple line. Has a slope of 2, a y-intercept of 0, 3. Easy enough to graph. Y-intercept of 3, slope of 2, you get some kind of line like that. So what if I wanted to look at it as a polar equation rather than a linear equation? Well, a couple of the formulas that come in handy are going to be are going to be x equals r cosine theta, y equals r sine theta, and x squared plus y squared is equal to r squared. Those are the most common ones to convert them back and forth. So since I want to create r's and thetas out of this x and y equation, I'm definitely going to use the first two. So if I do that, we would get y is going to get replaced with r sine theta. X is going to get replaced with r cosine theta. And then we have that plus 3 kind of just tagging along. So the goal here is to solve for r, if you can, if it's possible. So the first technique would be to get the r's on the same side of the equation. So I'm going to move this guy over to the other side. So this becomes r sine theta minus 2r cosine theta plus equals 3. Equals 3. Now we're trying to solve for r, and r is in two different locations. It's here and it's here. So the technique you want to use is just factoring. So you're going to factor out an r and see what's left behind. So we're going to get r times sine of theta minus 2 cosine of theta, and this will equal 3. So if I finally solve for r, I'm going to get r is equal to, and divide both sides by him to get it away from the r. So you're going to get 3 over sine of theta minus 2 cosine of theta. And the graph of this in polar coordinates, plugging in thetas and generating r's, would be the exact same thing as graphing this in rectangular coordinates. So both of them are the representation of a line with a slope of 2 and a y-intercept of 3. Kind of cool. Start talking a little bit about polar graphing and show you kind of what's going on. So our equation, of course, is 2x plus 3, which would give you a nice little line starting at 3 and having a slope of 2. But the other equation was 3 over sine of theta minus 2 cosine of theta. So here I have theta, in this case, is equal to b. And when theta is equal to 0, remember sine of 0 is 0, and our answer would become negative. So this point here that this is pointing to is the first point of our graph when theta is equal to 0, r is equal to whatever this point is, negative 1.5, 3 over negative 2. So as I increase b, the sine of this angle is going to be less than the cosine, 2 cosine of this angle. Therefore, we're getting these negative radiuses that the green arrow is pointing as an angle, but it's the negative radius of the negative terminal side of the angle. And the blue line is literally the line that's being graphed. Now, when we get to an angle where the sine is bigger than 2 cosine, it suddenly becomes positive, and it switches up here and starts drawing the picture from up above. But when it finishes, when the A comes back to where it started, we have a complete line that has a slope of 2. Oops, wrong coordinates. And goes through the point 3. So it's up 1, up 2, over 1. That's the slope of 2. So this is basically what polar graphing does. It kind of rotates and draws a point at the end of a radius. Kind of neat. All right, let's look at an example of a circle. X squared plus y squared is equal to 4. This is the equation of a circle that is centered at 0, 0, because there's no numbers next to the x and the y, and the radius is the square root of 4, better known as 2. So if we go through our formulas and try to find one that's going to work, we have x equals r cosine theta, y equals r sine theta, and we can use these if you want. It just makes things a little messier. And then the third one, x squared plus y squared is equal to r squared. That one seems the easiest because we have an x squared plus y squared, and we can replace it with r squared. So if we do that, this piece here, all of that becomes r squared, and it's equal to 4. And then if we square root both sides, we get r is equal to 2. So this is the polar form of a circle. And the nice thing about it It's much simpler than x squared plus y squared equals 4. It just says the radius of this thing is 2, and then because the angle can be anything, it wraps around the origin from a radius of 2. So that's one of the nicer things about polar coordinates. It changes circles into something easy to work with. All right, let's go the other way. Let's say we have r is equal to 4 cosine of theta. We'll see what kind of graph comes out of that one. Now, again, the substitutions are x equals r cosine theta, y equals r sine theta, and x squared plus y squared is equal to r squared. Well, I don't see how any of those are going to work because I have a cosine theta, it's right here, but I don't have an r in front of it. And I have an r, but it's not squared. So the trick that we're going to use here is we're going to multiply both sides by r. So we're going to get r squared is equal to 4r cosine theta. And it gives me the two things that I'm looking for. Number one, it's going to give me my r cosine theta, and that matches up with this guy up here. And then this over here being r squared is going to match up with this guy, and I can do a nice little substitution. So converting from polar to rectangular sometimes requires a little bit of legwork. So r squared, we're going to replace it with x squared plus y squared. The 4 is not going to change, but the r cosine theta becomes x. So that turns into the rectangular equation that looks like this. But I still don't quite know what this is. So I'm going to get the x's next to each other. I'm going to leave a space because I know what's happening. And it's going to equal 0. So if you remember from circles back in Math 171, there's this thing called completing the square. So if we complete the square on the x's, we're going to take half of negative 4, which is negative 2, and the negative becomes important later on. We're going to square it, and if we square negative 2, we're going to add 4. Now, if you add 4 to the left-hand side of an equation, you have to add 4 to the right-hand side of the equation. Now, the whole purpose of completing the square is to create a perfect square. So this one becomes x. The negative 2 just drops right down into the parentheses. This is going to be squared plus y squared is equal to 4. So this is a circle, and the radius of the circle is 2 because of this 4. R squared is equal to 4, therefore r is equal to 2. And the center is going to be opposite sign of x minus 2, which would be 2. And there's no number next to the y, so 0. So this graph of r equals 4 cosine of theta is just the circle. I'll try to draw a nice picture here. Whose center is at 2, 0, which would be over here, and then has a radius of 2. So that would go back to the origin and draw around the circle a radius. When it comes to polar graphing, I just do it in general form, the general idea of how to graph a polar equation. I would personally use technology to graph most of them because some of them can get kind of complex. So here's basically what you would do. You would do a table, and you would choose angles, and this graph is built on pi over 12. So this distance is pi over 12, this angle is pi over 12, and so forth and so on. So we're going to go by pi over 12. Why not? So 0 is a good place to start. So I'm just going to use my calculator a lot for this one. So I know the sine of 0 is 0, so this answer is just going to be 3. So if I plug in pi over 12 into my calculator for this mess, make sure your calculator is in radian mode, and then just type in 3 minus 3 sine of pi over 12. So 3 minus 3 sine of pi divided by 12. And we get 2.2. And I'm only going to round to the nearest tenth because this graph that I have over here is not going to be very precise. All right, and then 2 pi over 12, better known as pi over 6. So change this to 6. And I get 1.5. which makes sense because sine of pi over 6 is a half, so that would be 3 minus 3 halves. And then 3 pi over 12. All right, up arrow, oops, insert 3, 12 is going to be 0.9, approximately 0.9. 4 pi over 12, also known as pi over 3. So let's see here. Just change it to 4. And that's about 0.4. And then, let's see, that's 1, 2, 3, 4, 5 pi over 12. Change it to 5. That's about 0.1. And then 6 pi over 12, which is the same thing as pi over 2. Sine of pi over 2 is equal to 1. You're going to get 3 minus 3, so that brings us to 0. All right, so on the graph itself, let's go orange. We're going to plot 0, 3. So 0, 3 would be 0 radians. It's not 0, 3 that is here. This would be xy coordinates. This is our theta coordinates. So we're talking about a radius, an angle of 0. Oh, I wrote the point backwards, actually. It's supposed to be r theta when you write your coordinates. So the coordinate is r theta, even though you plug in theta to generate r. 3, 0. So it's not in the order that it is over here. I have to switch them because for some reason they chose to put r first and theta second. Not my choice. So r being 3 and the angle being 0, this is 0 radians lying along the positive x-axis in this direction. So that's where we have to start for the 3 is going to go 3 in that direction. So this is our first point. So that would be 3, 0. The next coordinate is going to be 2.2 pi over 12. So to get to pi over 12, that's this first angle. So that's the terminal side of the angle. And we're going to go out 2.2. So 2.2 is about, here. All right, and then the next coordinate would be 1.5 pi over 6, which would be along this terminal side here. And we're going 1.5, so this is 1.5 right here. The next one would be 0.9, 3 pi over 12. And that would be almost 1 along this side, terminal side, one more dash rotating around. And then we get 0.4 pi over 3. So it's one more dash and a little bit closer to the origin. And then 0.1, which is almost at the origin. And then we get down here to 0 pi over 2. So this is our terminal side. But that's not going to matter because we're not going anywhere along that radius. And we're literally at the regular xy origin. So this would be the first part of this graph. It looks something like that. All right, and then we can continue on and come up with other points. So it seems like the important points are going to be like the pi over 6, the pi over 3, the pi over 2, and the pi over 4. And, of course, like a 0. So the next one I'm going to do is not 5, 6, 7 pi over 12. I'm going to do 8 pi over 12, which reduces to 2 pi over 3. And then I'm going to type that in my calculator. And it's 0.4. 0.4. So it looks like it's just going to unwind itself kind of symmetrical to this one. The next angle I would choose is 3 pi over 4, which would be 9 pi over 12, 3 pi over 4. That's 0.9. That would correspond to this one up here. And then 3 pi over 4, 5 pi over 6 would be the next one. And that would generate probably the pi over 6, 1.5. And then the 0 angle would be pi, and that would go out 3. So if we plotted those points rather quickly, we would get along this line right about here. Dang it. Right about here. And then we would have 1.5 right about here. And then pi is 3. That's definitely over here. I'm sorry, this should have been 1.5. That would be here. This other one is 0.4. 3 pi over 4 is 0.9. It's really close. That first one should have been 0.4. Get rid of that one. So this one would be 0.4. Stupid program. 0.4, 0.9, 0.9, and then we would have our curve looking like this. Here. All right, so the interesting part happens in the bottom part of this graph, and I'll just give you a quick heads up of what it would look like. When sine is at terminal side here, 3 pi over 2, it becomes its smallest at -1. And then the 3 minus 3 sine of 3 pi over 2 would become 3 plus 3, which would be 6. So we're going to get a point that's down here. And the graph kind of looks like this. Kind of like a heart, but it's not as pointy at that point down there. So using a graphing program, I built this to show pretty much everything. The dotted line here, going off in this way, is the terminal side of the angle. The dark arrow here is the radius of measurement that we're going to go out. So when the angle is equal to 0, b being my angle up here, then I'm plotting this point here, 3, 0. Radius of 3, angle of 0. So as I open up my angle, I'm getting the other points, and that point is dragging and creating a curve. So here my angle when I get up here to the top is pi over 2 when it hits this point, right there. And then it bounces off and starts becoming, the 2 pi over 3, the 3 pi over 4, the 5 pi over 6, and then back to pi. So that's what I showed in my previous video. And then as it wraps around, it's going to do that dip down to -6. But the radius is equal to 6 here. So this is the angle 3 pi over 2. And it's down 6, but still it's on the positive terminal side of that axis. So that's a positive 6 radius. And then it wraps around and comes back to form the rest of the curve. So this is kind of a cool polar graph. It looks like a circle with its side pushed in a little bit. Another example of polar graphing. This is the function r equals 3 sine of 2 theta. So again, b is my angle theta, and the green dotted line going off to the right is the terminal side of the angle. And the first thing to notice as I open up this angle is the radiuses start to be positive throughout this part of the graph. So the dark arrow here, of course, is the radius as my angle opens. And we calculated inside that, 3 sine of 2 theta. And it shapes up like this. Now, I've changed the color of the radius here because now the terminal side is in the second quadrant, but my radius being negative has to go the opposite direction. So it's plotting on the opposite side of the terminal side of the angle. And we get this other shape in the fourth quadrant when we would expect it to be in the second. And that's only because in the second quadrant, sine of 2 theta turned out to be a negative number. All right, and then as we wrap it around past pi, it goes back to being a positive radius. And then as it goes past 3 pi over 2, it becomes negative again. And we get this cool picture that looks like a 4-leaf clover.